talk of today's session. Our speaker today is Omar Knio, who's currently the Dean of SEMSI and a Professor in Applied Mathematics and Computational Science here at KAIST. Omar has had a wide variety of prestigious positions, including at Duke and Johns Hopkins, and he's very well known in the research areas, amongst others, of uncertainty quantification, Bayesian statistics, computational fluids, and optimization under uncertainty. Omar has written of the order of 450 articles, books, conference proceedings, etc., and with over 13,000 citations. Omar is going to speak to us today about discrete and continuous time data assimilation with noisy observations. Please take it away, and thank you for coming.
Thank you very much, AJ, for the introduction, and thank you, Raul and AJ, for the invitation. Can everybody hear me, or yes? Thumbs up. Okay. So I want to talk a little bit about continuous and discrete and continuous data assimilation, and the focus is on noisy observations. And what we want to see is essentially how do assimilation scheme work when the data that we're feeding into the trying to assimilate into the model, or more precisely into the forecast, are uncertain or noisy. Just to make sure that I give credit where it's due, all of the work that you're going to see today is the work of Abdurrahman Hamoud, who's here sitting at the left, and this is part of his PhD thesis. And this is collaborative work with Ibrahim Hotait at KAUST, Driss Titi at the University of Cambridge, and Olivier Lemaitre at Polytechnique CNRS. And this is really part of a recent CRG effort that started last year. All right, so quick introduction. The setting that we are ultimately aiming at in the project is in the framework of a GCM, of a weather forecast, for instance, using a MIT GCM or the weather research and forecasting model, the so-called WRF model. And in this setting, the dynamics are quite difficult. They are complicated. The system has broad time and space spectra of instabilities, and it's really essential to be able to get reasonable and accurate forecasts to be able to assimilate observational measurements. Generally, we don't have measurements or observations are at extremely small scales. So what we need to deal with is taking coarse data and try to inject it into our computations or in our model forecast. And we'd like to do it in such a way that we are able to recover the fine scale dynamics. So if you have a hard time pinning down this mental picture, this is what you see in the form of a local weather forecast at the at the news in the evening, where you are presented with a weather map that shows a fine scale forecast, and the way it's generated is by taking a coarser model and generating the fine scale dynamics. There are two main avenues at downscaling coarse observations. Statistical methods, which I would say nothing about today, and dynamical downscaling. Dynamical downscaling is the focus of the talk, and it comes in two forms: either grid nudging and spectral nudging, and I will focus on the former. Okay, so we're going to consider two different algorithms. One is fairly well established by now, even though the methodology is new, and we call it continuous data assimilation. And it is essentially a dynamical downscaling algorithm that constrains the large-scale solution of the system so that it matches the coarse scale measurements or the coarse scale observations. And it's really essential, and there are quite a bit of technicalities that turn out to be key to be able to prove convergence that is really essential in order to obtain converged solutions. So the way that CDA accomplishes this is by introducing into the governing equations of motion a forcing term whose function is to drive the coarse scale observations towards to drive the coarse scale solution towards the coarse scale observations. And what we know about this machinery is that if you feed it with perfect information and subject to technical conditions that I will only allude to, but the technical conditions turn out to be essential, the downscaled solution is guaranteed to converge exponentially fast to the true solution. With noisy measurements, we also do have a theory, and the theory says that, again, subject to these technical conditions that I will allude to, the CDA downscaled solution will asymptote to the true solution with a tolerance, and the tolerance is proportional to the trace of the covariance of the observations. So this is really what theory tells us, and we'd like to see how we put that in practice. Now, in a weather forecasting, for instance, setting, we really can't implement always because the calculations are very heavy. We cannot implement the smoothing operators that are essential in or an integral part of the CDA algorithm. And the philosophy is as follows: when the observations are available, then we drive the Coarse scale of the solution towards the Coarse scale of the Coarse scale observations, and it is done in an essentially an impulse-like manner. So this is essentially the main difference between the two algorithms. So the goals, at least of the study, that I will try to summarize is we want to analyze the performance of both of these algorithms in a simplified setting, which is a setting of Rayleigh-Benard convection. And we don't want to just see, if we just have a noisy observation, but we want to generate a solution ensemble, and using what we know about the noise levels and the measurements in order to look at what a potential downscaled ensemble would behave like. We would want to look at the ensemble spread, and we also would like to look at the variance and the mean of the downscaled observations. All right. And lastly, I will touch a little bit on preliminary work on trying to do all of this with a neural network approach, and talk briefly about an outlook for ensemble-based data assimilation based on neural network. Basically try to capture this technology, maybe not to totally eliminate the need for ensembles in a forecasting setting, but to reduce the cardinality of the ensemble. Any questions so far? Okay, all right. So quick outline, few words about the Rayleigh-Benard systems, quick sketch of the CDA and DDA algorithm, CDA continuous data assimilation, DDA discrete data assimilation, and then talk a little bit about the numerical experiments. And when the when the situation calls for it, I will allude a little bit to the theory that I'm not doing justice to, but it's really an essential part of this of the implementation. At least as far as guiding the implementation, we're going to look at the impact of observation density and the effect of noise levels, and lastly, talk a little bit about assimilation using deep neural networks. All right. So this is the Rayleigh-Benard system, the governing equations. And if you're reading the system of equation, the first equation is what? For those at least who had part of the conservation of mass. All right, this is the most difficult equation of the three, because how it's derived is kind of tricky. The second one is F equal ma for a fluid. And the last one is the energy equation, which is really a transport equation, an advection diffusion for temperature. Okay, these are the equations of motion of a buoyant fluid. And the experiment that we have is essentially the one that we have in our room when we have a radiator or a hot wall. When we're heating from the bottom, the hot air tries to rise. When it tries, it hits a cold ceiling, and then it tries to fall down, and a recirculation pattern happens. The system is, characterized by two-dimensional grooves. The important one I want to focus on is the Rayleigh number. And the higher the Rayleigh number, the less stable the system is. And at high Rayleigh numbers, what we end up having is a broad spectrum of instabilities, in the sense that you do witness the formation of eddies of different scales, and of spatial length scale, and of different characteristic scales. this will become visually clear when we take a look at a few pictures. Any questions on the system? All right. All right. Any clue why I say the first equation is the hardest? It's really tough to derive. You know, this is one of those equations where if you go back to your undergraduate textbooks and you draw the little square with fluxes in and out, it's really not a convincing argument. It's, if you look at it, it's quite a bit of a circular argument, and you have to start with a Lagrangian statement of motion that, you know, says in the absence of relativistic or nuclear effects, the mass of a Lagrangian particle is constant, and that's the only way that I know of really rationally deriving this law. Anyway, the setup that we have in order to solve this equation, I'm going to focus on a two-dimensional rectangular domain, 3:1 aspect ratio. It has periodic conditions in X, no slipped conditions on the vertical top wall and on the horizontal top and bottom walls. And it has fixed temperature. The temperature at the bottom is larger than the temperature at the top, and so the system is unstable, and this is really what we want to do. So all of this is appropriately normalized. And the way that I initialize the system, I really don't know the initial state until I start looking at observations. So I'm going to start with a random sampling of the velocity and temperature, which really describe the field in uniform distributions of finite entropy. Okay. On the computational grid, you know, given the range of Rayleigh numbers that we have, I have a grid of high density. So you know, we are sufficiently dense, and with a second order scheme, we integrate it at very fine time steps. So essentially, we have something that is a surrogate of an exact solution in the sense that the numerical errors can be driven to be sufficiently low that for all practical purposes, as far as the analysis is concerned, we have the exact solution. The observation grid has its own step size, both in space and in time, and we observe at much larger, much coarser resolution in both space and time than we generally actually need to compute in order to be able to get an essentially exact solution. So we have two ratios, one that characterizes the ratio of H0 to H. H0 is the large grid size, H is the computational grid size, and S, which is delta T0 over delta T, this is the frequency in time that the observations do come in. Okay. Quick word about the CDA algorithm. So we don't have an exact solution. We are computing an approximate solution, which we call W. And this is essentially what I tried to state. I don't know if I have a pointer. I do have a pointer. So the core scale observations are called U0 and theta 0. Okay, and this is really the original system without these, the last term, which is what we use to drive the core scale solution towards the core scale observations. So this is a term that is proportional to the difference between U0, which is the observation, and W, which is the computed solution. And what is really essential to the theory is that we introduce an appropriate smoothing operator in space. So we just don't force at the grid where we are observing. Because if you just force the grid at which you are observing, then you know, you're just essentially doing the wrong thing, and the experiences say that convergence is essentially never achieved. Yes. No. Absolutely, and this. Yes. Yeah, yes. So this is really an interpolation operator, and it has to have the right properties. But essentially, we take a partition of the space, and we take the observations, or more precisely, the difference between the interpolated fine scale solution and the interpolated coarse scale observations that are essentially suitably interpolated in space, and we take the difference between the two as opposed to, yeah. Exactly. And then we introduced it. We do that in time in the case of continuous data assimilation. We do it discretely in the case of discrete data assimilation, and this is the primary difference between the two. So this source term in continuous data assimilation is essentially living over an entire time step until the new measurements come in, or it can be smoothed in time, but essentially it is there continuously in time until that would be essentially a zero order in time, or you can go first order, and essentially it is this way. But with discrete data assimilation, it's an impulse. That's the one difference between the two algorithms. So okay, and what theory tells us is that two key ingredients, and I don't question, no, okay, sorry. What theory tells us is that there are two key ingredients. Is that one, we need to observe in the dissipation spectrum. This is really not that surprising, okay? And then we have to have a gain that is high enough. In theory, the higher the better, okay? But in practice, we don't want to put it too high because that drives us to numerical instabilities, which is something that we really cannot tolerate. Okay, so these are the two ingredients. One has to do, you cannot just have one observation point and tell me something about the circulation around the Earth. You really need to cut in the dissipation spectrum, and then you have to drive the solution. You just cannot take this gain factor to be zero, so the gain factor can be large enough. And theory tells us at least where to start in the ranges of picking these gain factors. These mu's we typically tune at least in a range of dynamics, and once we tune them, we don't play with them anymore. No? They're really not that hard to tune. Okay. So DDA is a similar philosophy, okay, except here that these are impulses in time. Every time we have a measurement, we do the correction, and then the forcing term does not live between observation types. That's really the main difference between the two. Okay. All right. So what we know is that with perfect observations, the CDA algorithms has been analyzed quite extensively, and has been shown that if we pick the parameter right, then we drive exponentially towards the truth, exponentially fast in time, that is, towards the truth. And we tried computationally different order interpolants, and we found a very weak very weak dependence on the order of the interpolant. So you might as well stick with a zero or first order interpolant, because these are cheaper to compute. Okay. Also, theory tells us is that when we have noisy observations, then we are driving towards the truth, but we get there to within a tolerance. And in an expected L2 sense, which is really this skill factor, if you want, we are expecting an L2 difference that is proportional to the trace of the covariance of the observations. All right. Again, you know, we do have a nice theory for CDA in these. Okay. So here, what we try to see is what happens when we vary these noise levels. We're going to take white noise essentially. So this is just a variance term, and then we're trying to assimilate not one solution. So we're able to see, try to get an estimate of this expectation in an ensemble type setting. Without noise. So nowhere this is perfect observation. Everywhere you have them, but they're still coarse. If you have observations everywhere, you don't need a numerical solution, right? Yeah. No. We just they are coarse but perfect. The second case, they are coarse but imperfect. But the coarseness is obviously plays a role, and that's part of the analysis also. Yep. All right. So at least the computational study. All right. So we generate a noisy ensemble, and then we just don't downscale a single solution. We perturb this truth, and we generate an ensemble. And the noise level we vary, and we also vary the coarseness of the observation grids, both in time and in space. All right. So we are going to fix at least for the first set of experiments, the Rayleigh number, and look at different skill factors, which is typically what we use in weather forecasting. Oops. We're going to look at the root mean square error, a normalized version of the same quantity, the absolute error, which is really an average of an L1 type notion. We're going to look at the average ensemble spread, which is again a measure that we frequently use in environmental forecasting, in addition to this L2 metric lambda that I introduced in the previous slide. Okay, so this is how things look like. Okay, these are a few pictures on how the system evolves. The truth, I'm evolving from a state of rest. This is the high resolution calculation. And I'm showing you a few samples. All of this is at time equals 0. So there is nothing here that has been integrated. I'm starting from a noisy state. Here, I'm starting from a quiescent state. And in the true system, it's the instability, the growth of the instability that drives the subsequent dynamics. At slightly later time, and what I'm looking at here is the truth, and all the other frames are the errors in different samples. So this is the true solution. You know, when you heat the floor in your room, the hot air starts to rise, it hits the top, and the cold air starts to fall, and you get this complex recirculation pattern. And here we're looking at errors, so you can see that the scale is here by a factor of 10, which seems to indicate that even though we are starting from a totally random state, the system is really being driven towards the observation, and at even later time, the errors are, regardless of the initial conditions, we're essentially tracking, and the solution here has become really complicated with hot and cold filaments, and we're looking at the temperature, but there is quite a bit of complicated recirculation pattern in there. And the errors in all of the solution, not surprisingly, they get to be concentrated at the regions of high gradients, and but all in all, we're able to track the truth, at least visually, in a reasonable fashion. Okay, so to basically make sense of the analysis, I'm going to start somewhere, and I'm going to define a nominal case, at least for these values of the variances of the noise. These correspond roughly to about 10% of the characteristic values of velocity and temperature. I'm going to start with a spatial grid where we observe 1 in every 10 computational grid, and the frequency of 1 in every 10 time steps, and 1 in every 5 computational cells. And so this essentially sorry about the typo, assimilation every 10 time step and 5 spatial steps. So here the 10 is a typo, and we're going to vary initially sigma t and sigma u independently, but then I'm going to conduct an experiment where the variance of the temperature observation is going to be varied independently of the variance or the noise level and the velocity measurements. And we're going to look at varying SNR and see how CDA and DDA compare. Okay, so we're going to start looking at a few skill scores for the nominal solution. And I'm looking at an ensemble of 50 downscale solution. And if I'm looking at the absolute error or the root mean square error or the average ensemble spread, then in all of these skill metrics, the algorithm is going to a state where, at least asymptotically, the error levels are quite small. This is at least an initial uh, indication that things are going in the right direction. And I'm going to look at the effect of the ensemble size when we look at actual integral quantity, and this is coming next. If I look at the behavior, compare CDA, which is on the left, to DDA on the right, we see that the convergence of the CDA algorithm is much smoother. But when we assimilate essentially in an impulse-like fashion, the behavior may not be monotonic. But interestingly enough, when things do asymptote and we're really tracking and we're very close to the truth, the error levels in CDA are slightly higher than the error levels in DT. All right. And now we start looking at the impact of noise. And what I'm seeing here are three plots for three different skill scores for DDA. And then in the last one, I'm comparing the behavior of CDA and DDA. And essentially, things are behaving like we expect them to behave. As you increase the noise level, the fidelity of the skill of the observation deteriorates. And with estimates of the ensemble spread, again, you have higher ensemble spread with the higher noise level, and your estimate of the average ensemble spread essentially converges as a square root of the number of ensemble, as you would expect in a Monte Carlo type independent realization type of setting. If I look at the behavior of CDA and DDA, then consistent with the theory, at least in this range of noise level, things are dependent quadratically on the variance, or sorry, linearly with the variance. Again, as we anticipate from the theory. And as we observed from previous cases, CDA has slightly higher values of lambda. This is really when everything has converged. Both of them are quite useful algorithms because the error levels are really low. But there is something that's a little bit funny in the sense that when the error level is driven towards zero, all of these need to go to zero. So there is something that is really a little bit odd and that is very peculiar, that needs a little bit of deciphering. It turns out to be a little bit delicate, and I will talk a little bit about this in the next slides. So let me look at effect of observation frequency. Everything that we have is really for the nominal case. Three cases here. Okay. Observation frequency, we observe every computational time step, or we observe every 10 computational time steps, or we observe every 25 computational time steps. Okay. And the less frequent the observation, at least after a certain range, okay, then you know the fidelity of the downscaled solution deteriorates appreciably. Okay. What's really odd in these results is that between s equal 1 and 10, there is the asymptotic error levels, okay, or as measured by this skill score, tend to be roughly the same. And if you actually zoom in at s equal 10, the error levels are slightly less than s equal to 1. Okay, we can zoom on all of this information in the slot. And what we see, at least for DDA, which again, this is the first three curves, when we are assimilating in an impulsive-like fashion, okay, you really don't want to bombard the solution at every time step. Okay, so here, essentially, you suffer a little bit if you start impulsively pushing the solution towards noisy observations, because the noise also has high frequency. What you would rather do is assimilate and let the system relax. Okay, so the behavior is really not that very monotonic. And then, but then if you increase it beyond a certain range, then you start having an increase in in the error level, again as measured by the skill score. Same type of behavior for the root mean square errors, and same type of behavior for the ensemble spread. And now if we compare the CDA to the DDA, again, as we increase the assimilation frequency, we see that there is really a crossover. And when we assimilate at every time step, CDA is actually behaving much better. So it gains because, again, there is a smoothing that is taking place in time. Whereas with an impulsive type, then before you get this asymptotic behavior, the behavior is non-monotone. Yeah. It also has to do with the muse, but really not that big of a dependence on the muse. Okay, it really has to do with it is really more dependent on that stretching or that coarsening parameter than it is on the muse. Again, because we are forced to pick muse that are large enough so that convergence will take place. We're really not interested in deteriorating the muse so that this is really not something that we compromise on. I guess if we drop the muse towards very low values, then we see a bigger thing. But we really want to observe this very rapid convergence to too large is we get numerical instabilities, and we stay away from that because it really forces us to integrate at very low at very tiny time steps. Yeah, and it increases this difference absolutely. All right, so this is on the observation frequency, and we can also look at effects of grid density and similar type of behavior. All of this is done with DDA. Then again, as we increase the R, this is comparing two different resolution. If I increase the spatial resolution with the temporal assimilation frequency being fixed, then we do have a deterioration and an increase in an ensemble spread. And the same thing is observed at both high and low temporal assimilation frequency. Okay, so we can look at a fixed value of the frequency of assimilation at the impact of the coarseness parameter, and we essentially again observe a cubic type dependence, and which is really it's really a quadratic dependence, which is really reflected in both for both CDA and DDA, and this is also something that is kind of expected and intuitive. All right. If we look also at the let me skip, at least in the interest of yes. Yeah. I have the truth and I know the noise level. Okay, so I pick many realizations of noisy truth and downscale them all, and then an interesting exercise is going to come, which is more interesting than this, which is unexpected. You will have data and you will just downscale that data. Yeah. Okay. And now your follow-up question has a follow-up slide. Okay. All right. All right. So let me try to introduce the things on the statistics. This is really where I start alluding to something. Is it really worthwhile forming an ensemble? And this slide says yes. Okay. So this is how the root mean square errors in both cases, and they're done for both CDA and DDA. They are done at different times so that we can see what's going on. This is how your ensemble scores. 3% relative error, not bad at all. But if you take all of these guys and average, this is what you get. Okay, so there is actually a something to be gained by downscaling many observations and forming an average, and it has something to do with how their statistics end up expressing themselves. And but this is really one interesting observation is why would you want to do that? Is because I would like to get an exercise of this sort. Now the follow-up question, okay. This is a summary of something that we already discussed. The follow-up question is that you're going to tell me in practice, you don't have the truth in order to perturb it, in order to downscale it. You have a noisy realization of the truth. And the question is, what can you do? And you can do still the only thing that is available to do is to perturb that imperfect input and then form an ensemble this way. And of course, you pay the price. Okay, so if you perturb the truth, this is really how your solutions are done, and this is what the average is. This is really not zero, but you can see that there is quite a bit of gain in skill to be had by averaging. And if you have an imperfect truth, then you pay the price. Okay, then you're really further away. But averaging gets you better than, and if this obviously not as good as if you had the truth and perturb. Okay. We have an idea of we obviously have an idea of the size of the perturbation because we're assuming that this has to do with the instrument that we have. All right, now in this particular system, again, theory tells us that we can do assimilation with velocity data alone. And it's actually really not that hard how to do that. If you had the velocity, you can take the velocity and plug it into the energy equation, and back comes temperature. So essentially, if you give me the velocity, I should be able to reconstruct the temperature. And this is, but it doesn't work the other way around. And we have quite a bit of, theory tells us that, and we verified it at least computationally. And the question is, what happens when we don't assimilate with temperature data and we just have noisy velocity observations only? Okay, so I'm observing a partial state, and theory tells me that these partial observations should be enough. But in this particular case, I'm looking at the impact of noise. So this is a little bit of a busy plot, okay, but it actually speaks quite a bit to what is being done in, if you ask my opinion, a barbaric fashion of people trying to just take data and throw it at the problem. Okay, so I'm fixing the velocity instrument. The velocity instrument is not perfect, but rather sharp. Okay, and here's where I said before, and the temperature instrument is sharp. Okay, what happens if I take the cheap route and buy a cheaper temperature instrument? Then I suffer. Then I suffer really quite a bit. Okay. Beyond a certain point, it's better to trash the noisy data, because this is assimilation without the data, than to include the noisy data itself. Okay. Makes you think about the trends in the recent thing that let's put databases together and say, wait a minute. Okay. You bring me data that is really not of sufficient quality, it actually makes my life more miserable. And you really need people in stochastic numerics and UQ and statistics to say, wait a minute, it's not a simple matter of we throw databases and we throw measurements and we throw instruments and we get something that is better, because in this particular case, once your instrument degrades beyond what it was originally, you might as well trash that temperature data because you have a much better skill without it. Okay. Do I have how much? Oh wow, I can talk a little bit about. I can do a lot of damage, and I introduce what Abed's been playing with neural networks at least. Okay, so I've been watching deep learning for many years, and refusing to even dip my toe in that swimming pool, because I still have actually quite a bit of questions about that. But here is really a very interesting setting, and the theory, I cannot do justice for it. But it says the following: if you give me a dissipative system And if you're doing observations within this technical conditions that we have, then there exists, okay, a unique deterministic mapping that maps the core scale observations, actually the history of an appropriate history of appropriate core scale observation towards the fine scale solution. In other words, there is a learnable object. That learnable object is not true in every single application that we have, but in the dissipative systems that arise in here and subject to the restriction of the theory, there is something called lifting function or determining form that guarantees the existence of that object. And once I knew essentially how that worked, then there is actually something that neural network may, if they are trainable and if they converge and if all of these other things that we can go after. So what I'm going to present in the next few slides is really work in progress along this avenue. Again, using CDA because we know how it works. It integrates dynamical equation. We know how it behaves with noise. At high noise levels, we know how it behaves when we change the grid density. And and then I'm going to start with the deterministic case and then see what a neural network can do for us. And again, using my best dynamical tool as a benchmark. Okay. So we're calling it CDA-net. I'm not going to talk too much about the details of the neural network or of its training for one particular reason, is that Abed has a poster on this, and then he owns all of these bells and whistles. The way it looks is this way. So what we are taking, at least this is interesting, only to explain what the input and the output are. So an input, we have a bunch of low resolution clips, okay? And we run through these different machineries. We inject this in a high dimensional space of features. We train the parameters of the mapping, and then we unroll that into forming a high resolution image. And there are quite a bit of algorithmic details that are built in. Again, consistent with the recent trends, the reason we call it physics informed is that the errors, or as they call it in the neural network community, the loss is a combination of regression error or regression loss and a PDA error and a PDA loss. Okay, so this is really the structure. Essentially, I'm looking at it as far as this presentation is concerned, a black box, but quite a bit has gone into building the black box and tuning its parameter. So we have a whole lot of many grids. I'm still dealing with the same system that I dealt with before. Quite a bit is done into breaking the image into 3 little images so that it can fit in the memory of the GPU. The important thing I want to say is that, okay, we're looking at the accuracy of our prediction by a combination of 2 errors. Again, we need to tune the parameter lambda. This is the difference between what the neural network is predicting and the truth. And this is essentially an expression of the partial differential equations, whose residual we can evaluate at selected points. And this is really what we're trying to do, is apply an optimization algorithm to pick the parameters of the neural network, so this overall loss is minimized. And any particular reason for the yes, and it's the similar thing that we do with UQ. It promotes a certain sparsity and gives us guards against overfitting, because the parameters of the neural network, especially when it is broad and deep, can be quite plentiful. So that's really the rationale there. At the end, we're still evaluating based on skill scores that are variance based, and this is something that we are used to. So we are still using the relative root mean square error. What parameter? No, y is the state vector, and gamma y minus f is the differential equation. So this is the discrete differential equation, and this is the regression error. Okay. Okay, so I want to tune the network so I have good regression, but I also want to respect the physics, and I cannot enforce it at every point because of the amount of data that we can fit in GPUs and what have you. But this is essentially the machinery that I have. In a perfect world, okay, what the determining form would do is it would zero both of these things. So mathematically, we know that there is a super high dimensional object that would take the coarse scale observation that will zero any kind of error, essentially, if the solution is smooth, and at least in 2D, the solution will be smooth, okay? And I cannot prove existence and uniqueness of Navier-Stokes, but fine, and it will zero it will satisfy the differential equation. Okay, yeah, 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 yeah. The sparse is really there are uh, the high dimensionality of the object itself. So there are lots of and we want to avoid overfitting, and this really has helps us achieve that. Okay. Again, looking at root mean square errors, this is a complicated table, but what I want to show is that when we vary the space and the time between essentially the same parameters, we didn't go as high up as 25 as we did in the previous case, then we're getting relative errors in both temperature, pressure, and both components of velocity that are reasonable. And as we've seen before, if you increase s and if you increase t, then the fidelity of the downscale field deteriorates a little bit. Okay, what we're doing with the neural network is something that we are not doing with the determining form. We're actually filling in the space, not only filling the resolution in space, but we're also filling the intermediate time steps. So we're actually being quite ambitious here. And at least the initial experiments are indicating that this is at least promising. How does it compare with CDA? Okay, well, I mean, CDA is our gold standard. And if you're solving the dynamical equation with perfect data, you can take the error. CDA is in red and the neural network is in blue. Both of them are doing the right thing in the sense that, you know, except when your grid is you're trying to fill in over big times and very coarse grids, okay, you're at error levels that are there, and you need to zoom in to see the difference. So things are really not as nice, or in the case of CDA, can be made perfect because things are exponentially going to zero. But here, essentially, the error levels that we have are not bad at all. Okay. This is a visual comparison, okay, at an intermediate time. Again, we're assimilating with not assimilating, the coarse resolution clip here is every 8 time steps and every 8 spatial time steps, okay? And I have a more detailed example. So this is really the input. This is the truth. This is a coarse image. This is a high resolution image. This is what you get with neural network. And this is what you get by integrating dynamically the equations of motion. And things seem to be working pretty well. And even at later times, and we're not only tracking the system, again, we're taking a low resolution clip. So several time steps and getting high resolution clip at the same time steps here. And with CDA, at least visually, we really cannot see much differences. And at later, even at later time steps, you know, where at least this is an instance where the dynamics are quite complicated. The CDA net, the neural network, seems to be doing a quite a decent job. We can do the same thing without temperature observations. Again, here I'm in a situation with perfect data, but here you can take a look at, see how coarse our input clip is. At least this is part of our input clip. Okay, this is really what the pressure field that is fed into the neural network. Again, this has to fit with the theory, so you just cannot give me one image and say what happens, but this has to be a succession of image because you really, again, the determining form says you essentially take a history. Practically, we need a large enough window, okay? But if that window is truly large enough, then this is the snapshot, the last snapshot of the input clip, and this is really what the truth looks like, and what the neural network prediction is yielding. It's not perfect. You can see some of tiny differences between the two, but overall, it's actually pretty accurate. Okay, and at different time steps, the idea here is to see how coarse these inputs are, and what we're able to fill in with this super resolution idea. Last slide that I have is to show, what would happen if you actually did all the heavy lifting that Abid did and did train a network. And we trained it at a Rayleigh number of 10 to the 6. We know that in this business, that at very high Rayleigh number, these fine scale dynamics should show a very weak dependence, typically a low power of the Rayleigh number. Okay, so what happens if you use the same object to predict flows that are a Rayleigh numbers 10 times smaller or twice larger? Okay, if you train the object, then you might as well go ahead and use it. We cannot afford to do that with CDA because we're taking observations and plugging them into equations. But but with a neural network approach, at least if the actual Rayleigh numbers are not in two different bands, then training one object means that it is still useful, even if the dynamical parameters have shifted a little. It's pushing us towards the right thing, and because the fine scales show weak dependence on Rayleigh number. Okay, if we were in a transitional Rayleigh number regime and we didn't have a dissipation spectrum, so the weak energies, they really don't do that. I don't expect things to do if we took it to a Rayleigh number of 10 to the 9, things will fall on their nose, but at least it shows that you really don't need to train at every single Rayleigh number, but maybe in a band of dynamics, then things are, the object continues to be useful even outside the range of the data that was used to train it. Okay. So finally, I just wanted to show that I showed some preliminary experiments with with CDA and DDA, and later, this is our first attempt at doing things with CDNet, which is the equivalent of that with neural networks. We are actually committing a sin, okay, and we've already fixed it, in the sense that with the neural network, we're taking a high resolution clip and ending up with a low resolution clip, ending up with a high resolution clip, but we lose the custody of what we've built. Okay, and that can be fixed in the sense that if we have built a high resolution data, then we might as well use it for the next assimilation window and the next assimilation window and so on. And that turns out that it improves predictions appreciably, at least in the way things are converging. But what we still need to do is really much remains to be done in this area. We need to push things into higher dimensions. Ultimately, our goal is to get into a 3D GCM. We're taking steps in that direction. We want to look at if we train the object, okay, then I can feed many noisy observations. Okay, then I can go back and doing things with ensemble and trying to do, what kind of statistics do you get with a trained network? Okay, and then the theory is on the theory side, we really don't have much results in time, and we're working with Dries on trying to push the theory. And on the neural network side, quite a bit needs to be done. both on trying to learn, the impact on how to pick the right network, how to tune its parameters, how to guarantee convergence. All of these questions are still open, how to enhance the training. And we're working on all of this. So if there are not too many rotten tomatoes and you invite me back, maybe I can talk if we make progress in these directions. Thank you much.
Thank you, Omar, for that very nice talk. Do we have questions from the audience?
I gave him a lot.
No, you're sure. We have one. Yeah. Hamza, please go ahead.
Thanks for the nice talk. It's very interesting. So what I felt from the simulations that you had, that you using relatively high number of observations. What I know in practice, according to my knowledge, for example, in ocean, we'll be having one floater that will give you the height of the water at one grid point in a big grid. And there are also satellites orbiting around the Earth, will give you 1 point every maybe 90 minutes or so. So do you have any comment on that?
I do have a comment, and I'm going to limit my comment in a way that the audience can relate to. The areas that I pushed in here have ratios of 25. Okay, what this says is that let's pick, if you give me observations on every 100 kilometers, I can downscale to a range of every 4 kilometers. And in a weather map, this is crazy, insane resolution. In the ocean, you need to go down to 1. But if you give me the large scale grid is 25 kilometers and you're downscaling to 1, then this is quite a bit of dynamics that you are enriching. Yeah.
Thank you.
Any more questions?
Okay.
No, if no more questions, thank you very much, Omar, for your time. Thank you. Post the session now at 5 o'clock in building 19. Thank you.